Welcome back, everyone. In today's lesson, we're going to be starting the Chapter 4 lecture note outline. So this is the first lesson in Unit 2, and we're going to start here talking about the periodic table and how it's organized. And since we're going to be learning a lot about the periodic table today, it's going to be really important that as you follow along with these lecture notes, you also want to have a printed copy of our periodic table. So if you haven't already, head over to Canvas, find the periodic table that I've posted there, and print out a copy. First, what exactly is the periodic table? Well, that's a great question. If you don't already know, the periodic table is our latest and best attempt at organizing what we know about all of the matter in the universe. Now, this particular periodic table that we're using here and all over the world is not the first version of an attempt at organizing matter in such a way. In fact, this periodic table is only a few hundred years old. It was developed by a scientist named Mendeleev in the 1800s, the late 1800s. Before that, our organizational attempts were largely incomplete. In what way were these earlier attempts incomplete? Well, you might think that, we just didn't know enough elements, or we didn't know enough about those elements in order to organize them properly. And it turns out that's not really correct. We actually knew quite a bit about a lot of different elements, even back in the 1700s, before this current periodic table came about. What we were really missing in these early attempts was the key to unlock the pattern in which we should organize the elements, the most natural order for those elements, in fact. Now, what exactly was this missing key that we finally found and unlocked our ability to organize the elements? It happens to be something we now call the periodic law. It says this: when the elements are arranged in order, the properties of those elements will repeat in a periodic pattern. Now, what this is saying is if we take all of the elements and we arrange them into a very particular order, that order happens to be something we need to talk about further, but if we organize them in this order, we can look at the properties of the elements and we'll see a pattern. Specifically, the pattern we see is a periodic pattern or a cyclical pattern. What I mean by that is if we start at element, say, 1, and we go to element 2 and element 3 and element 4, at some point we will get back to an element that's different than the first one, but will have its same properties. And furthermore, if we continue in this pattern, we'll increase the number of the element, we'll see a repeat of all of the patterns. So for example, if I continue my pattern here and I go to number 6, it would have the same or similar properties as 2. And then if we added a 7, it would have a similar or identical properties with 3, and so on. This is the nature of what we're calling the periodic law. And really what it's saying is that the elements exhibit this property, which is very interesting. Now, how exactly did we come up with this law, and how do we know that it has some truth to it? Let's first go into the details of how we actually arrived at this periodic law and this organizational system that we now have. As I mentioned earlier, the current iteration of the periodic table is based on an earlier version that was put together originally by a person named Dmitry Mendeleev. Dmitry Mendeleev was a scientist, a chemist, working in Russia in the late 1800s. And he was putting together a textbook for his first chemistry course there. And as a part of that work, he wanted to organize the elements so that he could present them in an organized fashion to his students. Now, as he was trying to put this organizational system together, he stumbled upon this periodic law. As Mendeleev was experimenting with different organizational systems, he decided to order the elements in a particular way. When he did this, he noticed that they arranged themselves into groupings based on their properties, like in this diagram that I've shown here. As Mendeleev started to observe this pattern repeat over and over, he realized this was a very special system for organizing the known elements. The real trick to this was what was the order that he placed the elements in that no one had done before. Well, it turns out he arranged them in order of their known masses at the time. So you might be saying to yourself that Mendeleev must have gotten it wrong, because we now know that we don't organize the elements by their masses, we organize the elements by their atomic number, that is, the number of protons in the nucleus of the atom of that element. The problem was, in Mendeleev's time, there was nothing known about the structure of the atom. This is before even the discovery of the electron, let alone the proton and the neutron. So instead, Mendeleev used the masses. And one of the main benefits of this organizational system is that it allowed Mendeleev to predict a number of things that we didn't already know. For example, this organizational system showed a number of missing elements. These missing elements were essentially gaps in his periodic table. Based on the location of these gaps, Mendeleev was able to predict many of the properties that were later confirmed when that element was discovered. For example, he predicted ahead of time many of the properties of germanium, which was discovered at a later date in 1886. Mendeleev predicted its mass, its density, how it bonded, meaning how many things would it bond to, and its color. As you can see, many of these properties, which were confirmed quantitatively, are very close to what he actually predicted. Now, if this is just a one-off incident, it could easily be dismissed as coincidental or guesswork. But Mendeleev did this time after time, and he got very famous for doing so. In fact, many people who thought they had discovered a new element would often try to get an audience with Mendeleev to see if he would confirm their findings. So that's one really important benefit that we get from this organizational system, is that we can correctly predict properties of yet to be discovered elements. Now, another really powerful thing that we get out of the periodic table is its ability to allow us to see trends we might not otherwise see. Now, because you're going to be learning about those periodic trends in this course, you don't know them yet, so it's hard for me to sell you on that point. But let's take a look at one quick example. I'm going to point you to a group here on the periodic table that you will learn later is called the alkali metals. The alkali metals include lithium, sodium, potassium, rubidium, cesium, and francium. And one of the very interesting things about this group is that all of these metals react very vigorously with water. And an interesting trend here is that they actually react more vigorously with water as we go down the group. So for example, when we put lithium into water, we get a small sizzling reaction. It actually produces hydrogen gas in small bubbles. And then when we put sodium metal into water, we get a much more vigorous evolution of that hydrogen gas. Because this reaction is exothermic, after a short time, the hydrogen gas actually ignites. This often causes an explosion. If we're brave enough, we can continue this experiment with potassium. Potassium is the next element down on the alkali metals. When potassium reaches contact with water, it immediately ignites. Upon ignition, a large volume of hydrogen gas is emitted, and soon enough, this will also explode. Now, continuing this experiment beyond potassium gets very dangerous. Incredibly small amounts of rubidium and cesium can be acquired under certain circumstances and then exposed to water. In all of these cases, we get massive explosions with a very small amount of material. Beyond cesium, when we get to francium, we're entering the realm of radioactive elements, and this is not a practical experiment to conduct for most people. So that's an example of one of the trends that we see on the periodic table when we've organized the elements according to their properties. We see a change in properties and a trend in that change of properties as we travel through a group. So that's an example of one way that the periodic table helps us relate chemical behavior that we see to trends on the periodic table. Now, this last point that I want to make is a little more subtle, so bear with me for a moment. Sometimes when we look at the periodic table, we might find something that's unexpected. And it's these very unexpected anomalies on the periodic table that might help us discover new things that we don't know already. As an example, let's take a look at one of those discrepancies on the periodic table, that is between the elements tellurium and iodine. What I want you to do is pause the video for a moment and see if you notice any discrepancy on these two elements, tellurium and iodine, which are next to each other on the periodic table. What you might have noticed here between tellurium and iodine is that the trend of masses continuing to increase as we go from left to write across this row is broken when we get to tellurium and iodine. So notice that tellurium has a heavier mass than iodine, yet it comes before it in the periodic table. Now, as I mentioned earlier, when Mendeleev was first constructing his version of the periodic table, when he would have placed these elements on that, you would have had iodine before tellurium if you're going by the masses. And remember that all Mendeleev had were the masses, so he would have necessarily had to put iodine in tellurium's place and tellurium in iodine's place. Now, can you imagine what kind of problem that might present? Exactly. Iodine behaves nothing like the other elements in the group where tellurium is. Instead, iodine has properties much more in common with the elements in group 7, fluorine, chlorine, and bromine. So when Mendeleev was organizing this part of the periodic table, he made a guess that the masses that were given at the time for tellurium and iodine were incorrect, because the chemical properties of these elements place them into the groups that we see them in now. What Mendeleev didn't realize, however, was that these masses were in fact correct. What Mendeleev was missing was the fact that the periodic table organization wasn't based on mass, but instead based on something else that was not yet known, that being the number of protons in the nucleus of an atom. So it turns out this discrepancy actually pointed at something much, much more important than the order of tellurium and iodine on the periodic table. It pointed to an entire new field of study, the subatomic particles known inside of the atom. So now that we've had an introduction to the periodic table, let's actually go into some detail on the different parts of the periodic table, what they're called, and what they mean. Here in the second part of this lesson, we're going to learn about the different families of elements on the periodic table. These are also called groups. In each case, we're going to learn some of the most important groups on the periodic table, and as we learn about those groups, we're going to learn their location, the elements that are in the group, and a brief explanation as to the name of the group. Also, we're going to start talking about charges for the different elements in certain groups. It turns out this is a very important feature that you want to be able to get from the periodic table, so I want to make sure to emphasize that clearly. The first thing to note about the periodic table is that elements are organized into columns and rows. We call the columns groups, and we call the rows periods. Today, we're going to be focusing on the columns or groups of the periodic table. The first group that we're going to talk about is called the alkali metals. Let's take a look at the periodic table and locate this group. So as you can see here, I've cut out the left-hand side of the periodic table. And it's right here in group 1A that we find our first group, the alkali metals. The alkali metals can be found in group 1A of the periodic table. We also often call this group 1. The alkali metals includes the elements lithium, sodium, potassium, rubidium, cesium, and francium. Notice that I've treated the element hydrogen in a special way. First off, notice that hydrogen is in a yellow box, and the other elements here are in a purple box. That highlights one difference between hydrogen and the rest of the elements in group 1A. Hydrogen is a gas, and the rest of these are solids. As we're going to learn throughout the rest of this course, hydrogen has other very special properties that place it within this group, but also somewhat above it. So yes, hydrogen is an alkali metal, but it also has other properties, and some of those other properties place hydrogen in other parts of the periodic table as well. Now, why is this group called the alkali metals? Let's talk about that. The word alkali is an ancient word that means something like burned plant ashes. It turns out that an excellent source for many of these metals is from the ashes of burned vegetation. But now let's talk about the charges of the alkali metals. The alkali metals as a group has a very specific type of charge pattern, and that is they are always found as either neutral atoms or as +1 cations. They're never found as anything else, like +2 or +3. It's always 0 or +1. So those are the alkali metals. The only other note I have to say at this point about them is that they're all explosive in water. So now that we've learned the first group on the periodic table, let's go to the next one. The next group we're going to talk about on the periodic table is group 2, or the alkaline earth metals. The alkaline earth metals are located here in group 2A. This group consists of the elements beryllium, magnesium, calcium, strontium, barium, and radium. The reason why we call this group of elements the alkaline earth metals has to do with the fact that they're found as salts and minerals in the Earth's crust. The word alkaline is a little more subtle, and it has to do with the fact that many of these salts form solutions in water that we would call basic or alkaline. Now, the charge trend of group 2 elements continues the tradition that we saw in group 1. In group 1, we saw those elements all had either neutral or +1 charges. In group 2, we see all of these elements can be either neutral, so 0, or +2 only. We don't see any elements in this group having any other charges other than 0 and +2. So for example, we might have magnesium neutral or magnesium 2+, but we'll never see magnesium +1. Also, we might see calcium neutral or calcium 2+, but we'll never see calcium +3 or +1 or anything else. The only additional note I might have at this stage is that the next new element, which would be element 120, would belong in group 2 and should theoretically have some of the same properties that other group 2 elements would have as well. So that's group 2, the alkaline earth metals. Let's continue forward and look at the next groups that we find on the periodic table. The next group of elements that we run into is actually a very large block of elements on the periodic table known as the transition metals. To show you what I mean, if we continue past our group 2A, those are the alkaline earth metals, we get to group 3B. And group 3B represents the start of the transition metal block, which extends all the way over to the group that started by zinc here in 2B. This is known as the transition metals. We can describe this area as the 10 inner groups from 3B to 2B of the periodic table. Needless to say, there are a lot of elements in this group, so we're not going to list them all, but here are a few examples. We have scandium, which starts the group 3B block of the transition metals, and then we also see things like titanium, gold, zinc, tungsten, and mercury. Now, why do we refer to these elements as transition metals? As you learn more about what makes a metal, you'll find that many of these elements also share those metallic properties. However, they're variable and transitory between the different elements in this group. A really good example of this variation in properties for transition metals happens to be the charge trend. Transition metals have a variable charge, and it often depends on the particular type of metal. For example, if we're looking at iron, we see iron can be neutral, +2, or +3. This is different from other metals in the transition metal block. For example, copper. Copper can be neutral, +1 or +2. This is different than what we saw in group 1 and group 2. In those groups, we saw fixed charges. Group 1 is always +1 or 0. Group 2 is always +2 or 0. Here in the transition metals, we don't see that kind of consistency. It changes from metal to metal. Now, as you're going to learn, some of the transition metals do have fixed charges that we can count on, and others don't. Later on, we're going to learn which of these metals are like that. For now, let's add this to our notes. Some of the transition metals are fixed charge types, whereas others are variably charged, and we'll learn those specifics later. For now, though, let's go to the next group of the periodic tables that I want to talk about, that is the chalcogens. Now, to get over to the chalcogens on the periodic table, we're actually going to skip over a few groups for now that we'll talk about later on. The chalcogens are located way over here in group 6A. The chalcogen group includes the elements oxygen, sulfur, selenium, and tellurium. The last element in that group, polonium, is radioactive, and we usually don't consider it much when we're discussing these elements. This group of elements is referred to as the chalcogens because when these elements form compounds with other elements, they form something that we used to call calxes, which are chalk-like, and this is where the word chalcogen comes from. The chalcogens have a consistent charge trend. They are either always neutral or always -2 ions. So notice that we've switched from having positive charges to now having negative charges. That's a very important thing to observe. So for a chalcogen, you can either be neutral or -2. So for example, oxygen can be neutral oxygen or oxygen with a 2 negative charge. The same goes for sulfur and the other elements in this group. One quick note I'll add is the word oxide and what it means. An oxide is a type of compound that consists of one type of element in a compound with oxygen. So we have two types of elements, oxygen and something else. So I've written here an element with the symbol A that could be really any element, and that is in a compound with oxygen that has the symbol O. Now soon you'll be learning more details about subscripts on these elements, but for now note that they can really be anything. So for example, we might have a compound with the elements magnesium and oxygen in it. Because we only have one type of element with oxygen, this definitely counts as an oxide. What if we had water? Is water an oxide? Yes, it's the oxide of hydrogen. We only have two types of elements here, hydrogen and oxygen, and that is definitely an oxide. What about this compound? This is called sodium hydroxide, and you might notice from the name, it's not an oxide. That's because it consists of sodium, oxygen, and a third element, hydrogen. So now that we've gone through the chalcogens, let's go to the next group of the periodic table on the next page. The next group that we encounter after the chalcogens is known as the halogens group. The halogens are located over here in group 7A. This group of elements includes fluorine, chlorine, bromine, and iodine. The last element in this group with the symbol At is astatine, and astatine is very rare. It's so rare, in fact, it's the rarest element naturally occurring in the Earth's crust. The origin of the name halogen comes from the fact that many of these elements are found as salts in the ocean. The word halo actually means ocean, and gen refers to the fact that that's where they're generated or made. Now, what about the charge trend for the halogen group? It turns out that the halogens are also very consistent in their charges. Halogens can be found as either neutral species or the -1 ions. So for example, you might find fluorine in its neutral state or as a -1 charge, but never -2 or -3 or positive. Chlorine is the same thing. It can be neutral or -1, but nothing else. This trend is continued for the entire group. One additional note about the halogens is that they all occur as diatomic elements. So if you go out there and you find some fluorine or some chlorine, you would find that there are two atoms in each of those molecules of the element. And now we come to almost the last group that we're going to talk about. That is the noble gases. The noble gases are located way over here in group 8A. It's the last group of the periodic table. The noble gas group includes the elements helium, neon, argon, krypton, and the radioactive radon. One of the most interesting things about the noble gases is that they are completely inert or unreactive. And this is why we call these elements the noble gases, because that word approximates their purity and inertness. One of the reasons why noble gases do not react with other elements is that they do not ionize or form charged species under normal conditions. This is also why we find these elements as monatomic gases. Now, even though noble gases are unreactive, it turns out we can learn a lot about chemistry through these elements. For now, though, let's look at the last groups of the periodic table and where they're located. The last two groups of the periodic table that we're going to talk about are called the lanthanides, or the rare earth elements, and the actinides. Those are the radioactive elements. Now you'll notice both of these groups are offset from the rest of the periodic table. The reason why they're offset is because if we stuck them where they belong in the periodic table itself would just get too wide, so we offset them down here. The lanthanide group starts with the element La, which is called lanthanum. The actinides start with the element Ac, which stands for actinium. The lanthanides are also called rare earth elements, and that's not because they're particularly rare, it's just that they're not very widely distributed. They're only found in a few places in high concentrations. One thing that's really neat about the lanthanides is that many of these elements form very strong permanent magnets. So these aren't the kind of magnets that will fade over time. For example, the element with the symbol Nd is neodymium. Neodymium forms very strong magnets, and I happen to have one in my office if you want to stop by sometime. It's so strong, in fact, that it's very hard to remove from the metal surface of my bookshelf where it's now sitting. It's these special properties like magnetism that give rare earths a very special place in our modern civilization. They're used all over the place in electronics, phones, and weapons. Now, the last group here is called the actinide group. We call the actinides because of their radioactivity. We'll learn more about those much later in the course. So looking back over this lesson, we've gotten a solid introduction to the periodic table. We've learned why it's periodic, and we've learned the names and locations of various groups on the periodic table. In the next lesson, we're going to learn more about how it's organized. We're going to learn, for example, the difference between metals, nonmetals, and metalloids, and then we're going to start learning how do we actually name compounds that are built from these elements. With that, I'm going to end this lesson. I hope you're doing well. Please let me know if you have any questions. Take care.